A rectangular dog park with area 500 square feet is to be enclosed by a fence and then divided into two equal parts by another fence parallel to one of the sides. Find the dimensions that will minimize the cost. How much fence is needed? Okay, so the idea here is I have a 500 square foot requirement for a dog park. That's how much area is needed. But I want to use as little fence as possible. So I'm going to make an assumption in this problem that all of the fence I'm going to use costs the same. So to minimize the cost, I simply need to use as small amount of fence as possible in terms of the length. So let's see if I can draw a picture of this dog park. Assign some variables, and then instead of minimizing cost, we'll try to minimize the length of fence we're using. So I have a rectangle, and I'll call one of the side lengths y and the other side length x. And then I'm supposed to divide the dog park parallel to one of the sides. And oftentimes when we're doing this, students will say, how do I know if it's the long side or the short side? And the answer is we don't right now. You could have just as easily drawn it the other way and called it x. Because the variable names don't matter, and in solving the problem, we'll find out whether x is bigger than y. So my picture right now simply might not be to scale. Well, I can write down a formula for the area. That would be length times width, x times y, and I can also write down a formula for length. I have 1, 2, 3 y's. I have 2 x's. The additional piece of information is the area has to be x times y is 500 square feet given. This is what's going to allow me to get this down to one variable. Y is equal to 500 over x. And so now the length of fence will just be a function on the variable x because I can replace y with 500 over x. So here's my function. And so now what I need to do is minimize this function, right? Find a minimum value. So this time around, I think I want to use the first derivative test for local extreme values and one of my first derivative number lines. The reason for that is from the statement of the problem, I can't tell you a maximum value for x really easily. So I'll do something else. I know that the square footage is supposed to be 500, but I really don't know anything about the lengths, so I don't have enough information. I will tell you that x has to be bigger than 0 because x is a length of fence. And of course, this function is not even defined at x equals 0, so I better probably tell you that x is bigger than 0. All right, we're going to need to take a derivative. So I'm going to rewrite my function slightly just to make it a little bit easier. All right, let's take a derivative. All right, so I have 2 minus 1500 over x squared. My critical points are where my first derivative does not exist or is equal to 0. Well, my first derivative does not exist at 0, but neither does my function. So let's see if we can find any other critical values. I'll add the 1500 x over x squared to both sides. Multiply both sides by x squared. And I have 1500 equals 2x squared. So x squared is equal to, let's see, 1500 divided by 2. 750. And so x, if I'm solving this equation, would be plus or minus the square root of 750. Of course, we know that x has to be positive. And so I'm going to go on and simplify under that radical. Plus or minus, and let's see, 750 is 25 times 30, so 5 times the square root of 30. And so my critical point is 5 root 30, which is about 27.4 feet. All right, so L prime. Let's talk about the signs of L prime. I know I don't need to worry about x's that are to the left-hand side of 0. My only critical point is 5 root 30, so I can try a sample point on either side. I think the easiest things to plug into my derivative to test sign will be x equals 1, because x equals 1 is almost always an easy thing. And on this side, something bigger than 27.4, that'll be easy to handle. Let's say x equals 30. All right, well, plugging a 1 in here, I'd have 2 minus 1,500. Well, that will assuredly be a negative value. And plugging in a 30, let's see, I'll have 2 minus 1,500 over 900, which gives me 1/3, which is positive. So I now know my function decreases to 5 root 30 and then increases forever after that, making this the location of an absolute minimum. This is a test for local extreme values, but because I know I'm decreasing and then always increasing, it's actually an absolute min. So, the dimensions that minimize the length of fence and thereby the cost are, well, I'm going to round here, 27.4 feet by, and this is where I have to remember some other information I had, right? I have found a value for x, and now I need to find a value for y. So 500 divided by 27.4, which is about 18.2 feet. And then I'm also asked to report the total amount of fence used. And I have many choices here for what to use to report that. I could use this function, this function where I just plug in an x, but I'm actually going to use my original statement that I have 3 times y and 2 times x. So x is what I found, so I have 2 of those, 2 times 27.4 plus 3 times y. About 109.4 feet. All right, so in this problem, we actually minimized the length of fence, and I'm making a claim that we've also minimized the cost. This is a great example of a situation that does come up in application, right? You're asked to make something or build something, but you need to keep the cost low.